I was tracing erosion patterns in sandstone formations, trying to understand why the lateral recession rates in parts of the Colorado Plateau didn't match what the standard models predicted for that type of rock, and at first it felt like a small inconsistency, the kind of thing you expect to resolve once you gather enough data. But the more measurements I collected, the more something else started to stand out, not the erosion itself, but a proportion that didn't belong to the process I was studying. The flat-topped mesas I was mapping weren't just wide compared to their height, they were wide in a very specific ratio, and that ratio stayed consistent even when the formations were separated by hundreds of miles and formed under different geological conditions. At that point, it stopped feeling like noise in the data and started feeling like something I was supposed to recognize, even though I couldn't immediately place where I had seen it before. I set the erosion data aside and kept the proportions, not because I knew what they meant, but because they didn't behave like geology. They behaved like something else. It took me longer than it should have to identify it because I wasn't looking in the right direction, and when I finally recognized the pattern, it didn't come from geology at all, it came from biology. The ratio matched the relationship between trunk diameter and stump height in large tree species, not loosely, not approximately, but within a range that made it difficult to ignore once it was seen. That was the point where I stopped looking at rock. I spent the next few days reading paleobotanical literature, instead trying to understand whether that kind of relationship had ever existed at scales larger than what we see now, and the answer wasn't speculative. The record already shows that tree-like organisms reached significant sizes at multiple points in Earth's history, from proto-taxities in the Devonian to the massive forest systems of the Carboniferous that produced the coal deposits still extracted today. So the idea of large trees isn't the problem. The fossil record already supports that. The problem is how far that scaling goes. Because in large conifer species, the ratio between trunk diameter and total height follows a predictable range, generally between 1 to 50 and 1 to 100, depending on species and conditions, and that relationship is not arbitrary. It comes from the physics of load distribution, from how vertical structures support themselves as they grow, and it allows you to estimate height from diameter within a constrained range that holds across documented specimens. Now take that relationship and apply it to a mesa. A formation with a measurable summit diameter does not just give you a shape, it gives you a proportion, and that proportion implies a vertical structure that is no longer there, not because it never existed, but because whatever defined that structure is missing. The calculation itself is simple, but what it suggests is not, and that is where most people stop, because the implication feels too large to follow through. Geology explains these formations as the result of erosion deposition, and in some cases, igneous processes, and those explanations are supported by chemical analysis and field observation, but they describe how the material behaves, not necessarily why the proportions repeat. The ratio itself is not explained, it is absorbed into the model as coincidence, as something that happens to appear when multiple processes overlap. And that's where the question stays open. Because the ratio is measurable, the formations are still there, and nothing in the standard explanation requires that those proportions should match something biological in the way they do. At that point, the theory doesn't ask you to believe anything yet. It asks a simpler question. If the proportions match, what are we actually looking at? Once the ratio is there, the next thing that starts to matter is whether it's the only thing that doesn't behave the way it should, because if it is, it can be dismissed, but if it isn't, then it becomes part of something larger. And that's where the geometry comes in, because the proportions are not the only feature that repeats across these formations. The internal structure begins to show the same kind of consistency even when the formations themselves are classified differently. The most visible example of this is the hexagonal pattern found in columnar formations, a geometry that is already well understood in volcanology. When lava cools evenly from multiple directions, it contracts and fractures in a way that produces hexagonal columns, a process known as columnar jointing, and this has been confirmed through both observation and laboratory modeling. That explanation is not disputed, and it accounts for formations where igneous activity is clearly documented. What complicates things is where that same geometry appears outside of that context, because the same hexagonal structure shows up in places that are not classified as igneous in formations, where the official explanation is sedimentary, not volcanic, and where the cooling process that produces columnar jointing is not part of the recorded history. The geometry is still there, the structure is still visible, but the mechanism used to explain it is different. That alone doesn't prove anything, but it does introduce a question, because the same pattern appears in another field entirely. In biological systems, similar hexagonal structures appear in plant tissues and other organic formations, where stress distribution and energy efficiency produce repeating geometric solutions. The same physical principles apply, minimizing energy while maintaining structural integrity, and that convergence explains why similar shapes can appear in different systems. But convergence doesn't usually produce identical context, and that's where it starts to feel less stable. Because here the geometry is not just similar, it appears in structural positions that align with the proportions already observed, and once those two things overlap, ratio and geometry, it stops feeling like isolated coincidence. It starts to feel like multiple constraints pointing in the same direction. That direction becomes clearer when you stop looking at the surface and start looking below it. Because if these formations are what they appear to be in the theory, then the structure doesn't end at the visible boundary. A tree of that scale would not only have a trunk, it would have a root system proportional to that trunk, extending laterally and vertically through the substrate in a way that leaves measurable effects behind. And those effects do not disappear when the organic material is gone. Root systems change the ground they grow in. They alter chemical composition, increase carbon concentration, shift pH levels, and modify mineral distribution across every layer they occupy. And those changes can persist long after the physical roots themselves have decomposed. Soil scientists use these signatures to identify former root systems decades or even centuries after removal, mapping structures that are no longer physically present. That means the question is not theoretical, it is physical. Because if the structure above ground matches a biological proportion, then the ground below should contain a corresponding signature, something that can be tested directly. And the methods to test it already exist, from paleosol analysis to ground-penetrating radar, both of which are routinely used in archaeology, ecology, and geological surveys to detect subsurface structures and composition changes. And this is where the problem becomes difficult to ignore, because as far as the accessible record shows, those tests have not been systematically applied at the base of the formations in question, not because the technology is unavailable, but because the question has not been formally asked in that context. The instruments exist, the methodology is established, the formations are still there, but the specific test that would directly address the structural question has not been conducted. That absence does not prove the theory, but it does something else. It leaves the question open. And once a question like that is open, supported by measurable proportions, repeating geometry, and a testable prediction beneath the surface, it stops being something you can dismiss completely. It becomes something unresolved, something that sits just outside the current explanation, not contradicting it directly, but not fully contained by it either. And that is where the shift happens. Because at that point you are no longer just looking at shapes in the landscape. You are looking at a pattern that has not been tested where it matters most. Once the question moves from theory to something that can actually be measured, the next step should be straightforward, because if a structure above ground suggests a specific kind of origin, then the ground beneath it should either confirm or reject that suggestion. And this is where one formation becomes more important than the rest, not because it is the most unusual, but because it is the most studied. Devil's Tower in Wyoming has been surveyed, sampled, and analyzed in detail, and its classification is clear within the geological model. It is described as an igneous intrusion, a mass of molten material that cooled beneath the surface and was later exposed by erosion, and that classification is supported by chemical testing and structural analysis of the rock itself. The hexagonal columns, the vertical geometry, the cooling patterns, all of it aligns with what is expected from that process. That part is not in dispute. What becomes important is not the structure itself, but where it meets the ground. Because the boundary between the formation and the surrounding substrate is where the process that created it should leave its clearest signature. In confirmed igneous intrusions, that boundary typically shows evidence of thermal interaction. Heat from the intrusion alters the surrounding rock, producing baked margins, changes in mineral composition, and a transition zone that reflects the energy released during emplacement. That pattern is consistent across documented intrusions and is used as part of the classification process itself. At Devil's Tower, that transition zone is where the discussion becomes less certain, because the geometry of the contact does not fully match what is typically expected, and while the formation itself fits the model, the way it integrates with the surrounding layers leaves questions that are not fully resolved in the available literature. That does not invalidate the classification, but it does indicate that the explanation is not complete at every level. And this is where the two perspectives separate clearly. From a geological standpoint, the existing data is sufficient, the formation behaves like an intrusion, the composition matches, and any irregularities in the boundary can be attributed to variations in local conditions or incomplete exposure. From the opposing view, that boundary is the most important part, because it is the point where a different origin would leave evidence if it existed. That is not speculation, it is where the test should be applied. Because if a large biological structure once occupied that space, the substrate beneath it would not be uniform. It would carry chemical and structural signatures consistent with long-term organic interaction. And those signatures can be detected using methods that are already standard in other fields. Ground-penetrating radar can map density contrasts beneath the surface, identifying structures that are no longer visible, and paleosol analysis can detect chemical changes in soil layers that persist long after organic material has decomposed. These methods have been used to locate buried archaeological features, ancient road systems, and even root systems of trees that were removed centuries ago, producing measurable results from environments that appear undisturbed on the surface. Which brings the situation into focus. Because the formation has been studied, the instruments exist, the methodology is established, but the specific test that would directly address the alternative explanation has not been systematically documented at this site. That absence does not prove anything on its own, but it changes the position of the question because it is no longer something that can be dismissed as untestable. It becomes something that has a clear method of verification that has not yet been fully applied in the context where it matters most. And once that is the case, the discussion shifts again, because now it is not about whether the current explanation is correct. It is about whether it is complete, and completeness depends on whether all relevant tests have been performed. If a test exists that could narrow the question and it has not been conducted, then the question remains open by definition. At that point, the formations stop being just examples of geological processes and start becoming something else. They become places where a specific question is still sitting in the ground. By the time everything is placed together, the ratio, the repeating geometry, the biological scaling, and the absence of a direct test at the base, the question no longer sits in one place. It sits across the entire pattern, because none of these elements exist in isolation and none of them cancel each other out. The geological model explains how these formations behave, how they form, how they erode, and how they are preserved, and that framework holds, but it does not fully close the loop on why certain proportions and structures repeat in the way they do across formations that are not supposed to be directly related. That gap is small when you look at a single formation, but it becomes harder to ignore when the same pattern appears again and again across different regions, different classifications, and different geological histories. At that point, it stops being about whether any one explanation is wrong and becomes about whether the explanation is complete, because completeness depends on whether every measurable feature is accounted for, not just the ones that fit comfortably within the model. What keeps the question open is not speculation, but the fact that it can be tested in a specific way that has not yet been systematically documented at the locations where it matters most. The methods exist, the formations are still there, and the measurements that raise the question in the first place are part of the public record, which means the question is not hidden, it is simply unresolved. And unresolved questions do not disappear. They remain in place until something addresses them directly, either by confirming the existing model more completely or by forcing it to expand. That is what makes this different from an abstract idea, because it does not require belief to exist. It only requires that the measurements, the structures, and the absence of a specific test all occupy the same space at the same time. Because if the proportions are real and they are measurable, and if the geometry repeats in ways that extend beyond a single classification, and if the substrate beneath these formations can be tested using methods already proven in other contexts, then the only missing piece is not data, it is the application of that test where the question actually is. And that is where everything settles, not in a conclusion, but in a location, at the base of the formation. Because whatever these structures are, whether they are exactly what the geological model describes or something that requires a different interpretation, the answer is not on the surface, it is in the ground beneath them, in the layer that has not yet been fully examined in the way the question requires. That is the part that remains constant. The formations are still there, the measurements are still the same, and the question is still sitting exactly where it was when it was first noticed. If you're the kind of person who pays attention to patterns that don't quite resolve, if you notice when something fits almost perfectly but not completely, then you already understand why this doesn't go away once you see it. This is Tartaria Revealed. And the point is not to replace one explanation with another, but to follow the question to the place where it can actually be answered, because sometimes the most important thing isn't what we've already explained, it's what we haven't tested yet. And in this case, the answer hasn't moved. It's still in the ground.